different topics. And to start off, we have Joseph Boutros from Texas A&M and University at Qatar, and he'll tell us about cryptography and channel coding.
Thank you, Chris. Good morning. Thanks to Chris, Daniel, and Daniele for the invitation, and thanks for the audience for being here on Friday morning. So let me start by this table. I had some fun this week making the table. It was not here 2 weeks ago. So I'm trying to compare coding theory and cryptography. So let's say in the larger fields, information theory and computer science, and what are the different parameters we use and the different criteria. So I'm not going to comment everything in the table. Some elements are maybe controversial, but let's say, yeah, this is the red and the blue and the red. First item about the probability of error. So you know in cryptography, we would like Bob to decrypt with 0 error probability. Now, we don't have 0 error probability in channel coding. There is no 0 error rate. This doesn't exist, and it means immediately this is going to be a bottleneck for cryptography. I mean, the place where you transmit digital information or the place where you store digital information, we cannot have 10 to minus 128. This is impossible. So this is a kind of bottleneck. So the numbers I put here, this is for voice, 10 to minus 6, this is for data, 10 to minus 9, let's say high definition video, 10 to minus 15 and below, let's say 10 to minus 20. This is for fiber optic communications. But we never have below that, and we don't try to do it in practice. Now, of course, in theory, and this is what in my main theorem I'm going to prove today, I would like this error probability to vanish, to go to 0. Now, the dimensions, 8,000 seems reasonable. So maybe twice this, sometimes 16,000. The same in practical applications. Today, I will show you 1 million. We can do 2 million. And of course, when we do analysis, we can let the dimension go to infinity, and we do analysis in both fields is the same. Okay. Finally, a point signal-to-noise ratio. It's not obvious. In information theory, we take into account the energy of a constellation. So when we have a lattice, sometimes we don't deal with the lattice as an infinite constellation. We carve a finite constellation, and the finite constellation has a finite second-order moment. So we call this energy. Now, there is something similar in homomorphic encryption, the threshold of the maximum noise you should have after many operations in homomorphic encryption. So this is maybe similar to some signal-to-noise ratio, but I'm not sure about it, because we don't have the notion of energy in cryptography. Okay? So I'm trying to open for the audience in computer science and cryptography. Leo, if you have a question, do not hesitate.
I'd like to comment on this notion of energy. So maybe in cryptography, we don't deal with the infinite lattice either. We actually quotient it by a super lattice. That's going to be, you know, ZQ to the end. That's what we're doing.
Yeah.
That's the way.
Indeed, but the Q is large. Yeah. You see, I mean, if we take the example of Wi-Fi, we never go beyond 256 points in Wi-Fi. So, okay, in DSL, but DSL is over because we're replaced by optical fiber, we can go up to 32,000 points, but there is no constellation bigger than this in practice. Again, in theory, we can let the number of points. Today, I'm going to deal only with lattices, infinite number of points in a constellation. Okay? So this is the model. Huh? Yes?
Comment / ask a question. This signal to noise ratio
yes.
is very interesting. So I feel that the main difference between the two between this notion between in channel coding versus cryptography is that in coding theory, you know, the noise is given by nature, and in some sense we don't want the noise, but you know we have to deal with it. And in cryptography, we're actually artificially adding the noise. So in some sense,
it's by nature, but also we have interference from other users in communication. So we have two types of noise. In cryptography, yeah, it's not the same as, yeah.
And it's very interesting because in the coding theory world, in some sense, the noise is given and you're trying to get rid of it. And in cryptography, you kind of want to add noise so that you can argue that it's secure.
Yeah, but this is the friendly noise for the MAC-Alice-like crypto systems. I agree, but here I'm talking probably about the noise generated when you do the encryption. Each time is homomorphic encryption, the noise level is increasing, and then at one point, it's not, yeah. So I mean, if you have other suggestions to improve this table, please do not hesitate. Send me an email. We can. I'm sure. I mean, these tables I wrote it this week, and every day I was modifying a little bit, having some comments. If you have further comments, please do not hesitate. Send me an email. Okay. So this is the main model, a really simplified model for information transmission using lattices. The encoding is not necessarily via a generator matrix for the lattice. It can be done differently, but here I wanted just to simplify. So Z, the information is in Z. And then starting, since the lattice is Z, the module in this case, from Z, I create X, the lattice point. This is the simplest channel model, Gaussian noise, additive white Gaussian noise. White means the components of the nodes are IID, are independent mainly, but we assume they are IID, and 0 sigma square. So this sigma square, I'm going to use it till the end of my, so this is the variance of the noise, of the additive noise on our channel. And then the decoder is here. So this is simply why I'm saying information transmission, because the idea is once you get X here at the decoder output, the idea is to get back to Z from X. Now we can define two different probability of error. So the first probability of error is the probability of error per point, per lattice point. Now, we like encoding, sometimes we call it word error probability, word error rate, because a code word of lattice point is the same vocabulary. And then we can also talk about the error probability per coordinate, per lattice coordinate. So this is when xi is different from xi hat. Okay? Now, today in the demo, I'm going to show you symbol error rate. I mean, probability of error per coordinate at the end of my talk and the demo. However, in my proofs, I'm only going to talk about the probability of error per point in our proofs.
Question.
Okay, yes?
Why is the SER even meaningful? I mean, if this is a real lattice,
Yes.
one coordinate doesn't.
Now, in between quotes, in modern, I mean, I don't like the word modern, but we are using it. In my title, I mean, what is modern today, in 10 years, maybe it's not modern anymore. So in modern channel coding, we use iterative decoding. Iterative decoding is locally oriented. It means you decode the symbol and the neighborhood of the symbol in the code. There is no global view. It's not like what we call maximum likelihood decoder or a closest point decoder. So in fact, the iterative decoding of the lattice is going to decode the lattice coordinate one by one. You see? So that's why at the end I get what we call the APP, the a posteriori probability of each lattice coordinate. And depending on that probability, we decide what is the value of the lattice coordinate. So then the SER is one of the parameters we use. Now, of course, usually when the SER is, I will show you, when the SER is going down, the WER is also vanishing. Now, in some applications, you may still have a big block, let's say a lattice in dimension 10,000, but only one coordinate is erroneous. In that case, what we do in coding, if I have an LDPC code and I have 2 erroneous bits, I plug a BCH code on top of the LDPC code. So here it's like, if the lattice is not enough, you put an extra layer of correction, of error correction, to help the lattice, okay? So, but I will show you later at the end of the talk. Okay, right now I would like you just to be sure that all of you understand this very simple model, and then the main theorem I'm going to prove is about this simple model. So I'm not going to consider finite constellation. No, I'm sorry, I have only 1 hour. I cannot talk about Voronoi constellations. So this is how we do the shaping in these lattices. We take a sub-lattice. So with Voronoi cell is bigger, and then we do the shaping using Voronoi constellations. You know, I'm not going to talk about finite, only infinite constellations. So, many questions. I'm asking 3 questions. I'll try to answer the 3 questions. First one, what is the maximal sigma square such that I have a vanishing error probability? Of course, you normalize the fundamental volume of the lattice. Let's say volume is 1. Second question, can we build a family of lattices that can achieve this sigma square? Okay, fine. Now, you know, it's like Shannon random coding. There exists 1948. We have good codes, but how to build them? So this is, in fact, here I'm asking, probably there are lattices to achieve the sigma max. I will call it sigma max. Can we build them? And then it's not enough. Can we decode these lattices?
So sigma
is the noise variance on the, yeah. So this is, here we are in n dimensions. So this is a vector, a noise vector in Rn. And each noise coordinate is n0 sigma square. And I assume they are IID. So the idea is, what is the maximum value of the noise such that you will be able to decode with a vanishing error probability when n goes to infinity? Okay? So these are the three questions. I'll try to give you proofs. In fact, I will give but you have to be patient because we have many lemmas before reaching the main theorem. Okay? I have also some nice coloring and some nice figures. Let's see. I try my best. First, let me talk about algebraic construction of lattices and how I'm going to build these lattices before giving you the sigma max. So I will talk about the sigma max. It's coming. But first, I'm going to talk about building good lattices out of error-correcting codes. So this was suggested in 1971 by Leach and Sloan. It's called construction A. So what do you do, in fact? You look at PZN. PZN has P to n cosets inside Zn. You select some of those cosets. How many? P to k. How do you select P to k? Using the error-correcting code C, I call it C. And it is of length n, the same dimension as the lattice. K is the dimension of C as a subspace of Fp to n. Okay? So we say dimension length, so we should not mix between, because the dimension of the lattice is the length of the code, but the dimension of the code is K. Okay? So this is how we do it. Now, I'm writing it like this. This is a simple formula that works well with Z. Now you have to be careful. Why? Because C lives in Fp, so it means you have to do some natural embedding from Fp to Z. That's very easy for Z. Of course, you can change the ring if you like. You can do Gaussian integers, Eisenstein integers, quaternions, Icosians. And even we saw it also this week. We can use number fields and the ring of integers and number field. Again, when you are here, you have to be careful. Here, you should put the homomorphism going from the finite fields into the ring. Okay, you cannot write it like this. But I'm writing the equation of lambda like this just for simplicity. Okay. Now, how can you see this this construction A formula? So look at the code. This is a P-ary code. So imagine a cube in dimension n, and the side of the cube is P. And then some points of the code are inside that cube. And then what do you do with the cube? You move the cube in all directions by P. You pave the space. You get a lattice. So this is how geometrically you can see construction A formula. Okay? And of course, near the origin, the lattice will get the same properties as the code itself. So if you know about how the Euclidean distance of the lattice is distributed around the origin, in fact, it's the same as the distribution of the code. The theta series is the same around the origin, up to P minus 1 over 2. Okay? Now, if we consider the number fields, of course, you have to put this phi. So the formula is like this. I put phi of C. What is phi? Phi is going from Fp into lambda OK. So the notation is the same. O is the big O, is the ring of integers in K in the number field. So here what do? We take the ring of integers. OK is similar to Z. And then we apply canonical embedding to get a lattice. Now, what did we do in construction A in Z? We are using PZ. What is PZ, in fact? It's an ideal of Z. We do the same in number field. We take an ideal I, we apply sigma to I, we get a lambda I. So lambda I is the equivalent of PZ, if you want, and OK is the equivalent of Z. And then you have similar construction A. So this is the PZ, lambda I, and here I have to embed Fp into OK. And this is an example with P equal 11. Okay, P equal 11, so this is a lattice lambda OK from Q square root of 5. And if I take the 3 first shells of the lattice, here I have 2 points, here I have 4, and here I have also 1, 2, 4, and the origin. You get 11 points. In fact, this is FP. This is FP in the plane. And then the blue points you see here, this is the equivalent of PZ. This is the ideal. And then what does it mean making construction A? It means the error correcting code will choose points just from here among the 11 points in F11. And then the plus ideal raised to M will move these points everywhere to get the whole lattice. Okay? The same as with that. Okay? Fine. Now, this is, I wanted to show you this slide. This is a slide I did 5 years ago, but I modified, I added, this week I added this line. So I'm trying to gather all possible construction of E8, just to show you that really algebraic constructions are wonderful and so rich. Of course, here this is E8. I'm not going to do a demo with E8 in dimension 8. This is too small. However, this is one of the most beautiful lattices, E8, and of course, lambda 24, the Leech lattice. So what you see here, this is construction A from the extended Hamming code, 844. Binary, P equal to 2. But my talk today is not about binary construction. It's non-P array, and I'm going to let P go to infinity. This is another construction using 2 error correcting codes. This is called construction B. It's not construction A. And here it's over the Gaussian integers, Z of I. You can also do over the Eisenstein integers, over quaternions. And then, of course, if you take the Icosian, it's directly E8 equal to Icosians. And here what I showed you, if you take the ideal, this is a special ideal, in fact. You have to take 5 OK, a principal ideal. You factorize that ideal, and you get this one. So these are the 2 OK generators. And this is a cyclotomic field 20. You do sigma I, you get E8. No need for construction A here. There is no construction A. It's just you take this cyclotomic field, you get E8. Okay. Yeah, so this is the beauty of algebraic constructions. Now, of course, today we want to let n go to infinity. Unfortunately, it will not be as beautiful as E8. So, but it will be beautiful in terms of graph theory. I'm going to use a lot the graph description of the code inside the lattice. Okay. Now, back to construction A. This is the generator matrix of the lattice when you use construction A. Okay, please remember construction A. Just remember this. Lambda is a P-array code you embed directly into Z plus PZN. Okay? And K over N is what we call the coding rate of this code. Okay? So the generator matrix of lambda after construction A is very simple, in fact. What you see here is the generator matrix of the code. And then you add the missing dimensions, P times the identity matrix N minus K. Okay. So now, do I need this matrix? Probably no, because today in my 1 million demo, I'm not going to use a matrix of 1 million times 1 million. No. Yeah, but this is a way, if you need, for small dimensions, this is how you get from the code to the lattice in terms of generator matrix. Now, of course, we have the fundamental volume of the lattice. This is obvious because P to N is the volume of PZN. And because you are translating by P to K different translates, so you P to N divided by P to K, you get the fundamental volume. And then we have a simple lower bound, upper bound for the Euclidean distance, minimum Euclidean distance of the lattice. Of course, it cannot exceed P square Y, because PZN is a sublattice. So this is what I showed you here. I showed you that PZN is inside our construction A lambda, and lambda is inside Zn. Okay? So it means if P is small, you make lambda weak. You cannot keep P finite. I cannot achieve the limit, sigma max, by keeping P finite. I need to let P increase. Now, by how much? If you look at the literature, in the literature, P increases as n to lambda. And lambda at least half. And most of the time greater than 1. So when I say literature, who started analyzing this? Andrea Lolliger in 1997, and then further 2004, Erez and Zamir in Tel Aviv, also they did it. So in all these analyses, it was n to lambda. P was n to lambda. What I'm going to show you today, I'm going to break that. I'm going to do P polylogarithmic, log n raised to a, and then we have a condition on a. So I have a much smaller P, okay, than what we were doing in the literature before. Okay, so what else I can say? And then, of course, the squared minimum distance normalized by the volume 2 to n. This is what we call fundamental gain of the lattice. By abuse of terminology, I call it the Hermite constant of the lattice. Okay, so this is related to the packing density of the lattice. It's not very important today. I will be able to achieve sigma max without having the best packing density, the best Hermite constant. Okay, so this is the sigma max. I'm announcing the sigma max without the proof of sigma max. I will prove how to achieve it. Okay. So this was discovered in 1994, but in fact there are two other also more recent papers talking about the same sigma max with different vocabulary. So in fact it's 1 over 2 pi e. This is what you should remember, 1 over 2 pi e. What is funny, this number 1 over 2 pi e, it's also, if you compute the second order moment of a sphere in n dimension, when you let n go to infinity, you get also the 1 over 2 pi e. So in some way, it's also related miracle to shaping, but I'm not talking about shaping today. And of course, if the volume is not 1, you scale by v 2 to n. So what is the sigma max? If, in fact, this if and only if. So it means if sigma square is greater than this quantity, whatever you do, whatever is the lattice, whatever is your decoder, the probability of error will not vanish. Okay? And then if sigma squared is less than sigma max, there exists a family of lattices, lambda n going to infinity, such that the probability of error is vanishing. Okay? Now, since we know the fundamental volume of the construction A, I plug it here. So this is our sigma max of construction A. And then I would like to approach the sigma max. I put some delta. So we're going to use sigma square equals sigma max 1 minus delta square. So the delta is on sigma. And then I would like to prove in my construction that the probability of error will vanish for any delta greater than 0. Yes?
So in the theorem that you have, it gives existence of some lattices that will achieve this.
Yes, but it's not constructive. We don't know how, yeah.
So, but down there, construction A lattices.
I'm just taking the formula of V, the fundamental volume, the volume of the Voronoi cell, from construction A, and plugging it here.
So these construction A lattices will not achieve the best possible sigma max.
They will. This is what I'm proving today, and this is my main theorem. Yeah, but I'm using a special code. I'm using a very simple code that I can also decode. Again, if you put a random code, you're going, yeah, so this was already proven in 1997, as I said, by Lolliger. If you put a random code where the parity check matrix is dense, you're going to achieve this limit, Poltirev limit. But how do you decode the random code? I don't know how to decode random. So today I'm going to show you a low density code. Now be careful when I say low density. It's about the sparsity of the parity check matrix. However, the packing density of the lattice can be very good. Even if I say low density, it's low density about H, not about the lattice. And then this code I can decode in practice. And it will reach sigma max using construction A. Okay?
What is R in the notation then?
R is the, yes, as I said, K over N, the coding rate. Yeah, so yeah, the choice of R is important. Why? Because from this simple bound, you can see that the Hermite constant is upper bounded by P to R. It's like if you take the coding rate too small, you're making the Hermite constant bad. I mean, it's going down. Now, what will happen to the main theorem I will show, P is going to be log n raised to A, and A to R is greater than 1. So we're going to have a behavior where the Hermite constant is increasing as log n. This is not the best. The best is n. So this is Minkowski in 1905. Gamma should increase as n over 2 pi e. The 2 pi e is coming back. So if you go back to 1905, Minkowski, there exist dense lattices. The gamma is going to be as n over 2 pi e, and then the max found by Gabatchansky and Levenstein, 1979, you get 1.744 divided by 2 pi e n. So these are the best lattices for packing. But again, I don't care about the packing. I want to reach the sigma max, the Poltirev limit. And you will see that I don't need n. Log n here is enough to reach the sigma max. Okay? So remember that R is k over n again, and k is the dimension of the code, and n is the length of the code inside the code within the construction A of our lattice. Okay? Fine. So I will give an interpretation of this bound, but before that, I need this lemma for my theorem. So this is well known as sphere hardening. In high dimensions, the volume of a ball is around the sphere. It's not in the middle of the ball. So here you take NIID Gaussian and 0 sigma square. In fact, this is our noise. It's the same as could have put theta here. And then the probability to be between sigma square root of n1 minus epsilon and sigma square root of n1 is 1. So it means in high dimension, the Gaussian noise is going to be like this. Almost a sphere. This is in high dimension. The proof is very simple, Chebyshev. We're not asking about very fast conversions. Here it's just 1 log n squared. But that's enough to prove that we have the sphere hardening effect in high dimensions. Yes?
Go back to the previous slide, so just to make sure I understand. So you said this is an existential result, so it doesn't give you the lattice. So actually, I'm confused by the meaning of decoding probability. Is it just the fact that you take a Gaussian noise, and what is the probability that this Gaussian noise stays within the Voronoi cell of the lattice?
Yes. This is, yeah, exactly. So if I go back, this is the probability of error per point. It's the probability of x different from x hat. So x hat is what the decoder, let's say closest point decoder. So when you go outside the Voronoi region, indeed, you get an error. Now I'm going to deal with this without knowing the shape of my Voronoi cell, because our lattice family will be random. How? By using this ball, the ball of the noise. Okay, so let me go back to this. So what are we saying here is that the noise is behaving like this in high dimensions. So I have a noisy sphere, if you want. And I'm going to put this sphere around y, around the noisy point. And then if I have two lattices, two lattice points inside the sphere, the noisy sphere, it means I may have a mistake. If I have a unique lattice point, then I'm good. I'm decoding well. You see what I mean? I don't need to know the shape of the Voronoi cell. Just I'm using so the noise ball, I'm going to call it the decoding ball. Why? Because I know that my noise is not going to go more than the sphere. So why do you need to know the shape of the Voronoi? No need to know the shape of the noise. So you receive y. Remember my notation. What is y? Okay, I'm sorry for, maybe I should have put this in the simplest. Y is the noisy version of the lattice point. Okay? And again, I'm dealing with the infinite lattice. To simplify, what do you think if I transmit 0 here? Does it change the probability of error? Question. Is this probability of error depends on the transmitted lattice point x? No, because it's a lattice. You stand up on any lattice point, you look around you, you have the same landscape. So in fact, for simplicity, let's say x is 0. And what is y finally? Y is the noise itself. Okay? So now you have a noise around the origin. You will not go beyond the noise ball I'm talking about. N, the radius is sigma square root of n. And then all you need to do is to check inside the noise ball if you have another lattice point or not. If you have another lattice point, then there is a mistake. If 0 is the unique lattice point in the noise ball, there is no error. Okay, I will write it down later. Okay, so remember that in high dimension we have this sphere hardening phenomena.
Why is the ball and not twice the ball?
Okay. I'm transmitting 0. I have a noise, and this is y. Okay? So now what do? I do and now let me put the noise around y, the ball around y. Oops.
Oh, the
Sorry?
ball around
Y.
Around the received noise. Okay.
Yes, so this is b, y in dimension n, and radius is rho.
Okay.
Okay, sorry, let me draw it better than this. And here I have rho. Okay, imagine this is, I'm not using the Euclidean metric, okay? this is the Boutros metric, and I'm sorry. Okay, so you have the decoding ball around y. Okay, so you don't need twice this. Okay, now of course if I have another lattice point here, let's say x belonging to lambda, then it doesn't mean there is a mistake. Why? Because it's like list decoding. Now your decoder is supposed to choose, is it 0 or is it x? But again, it gives you an upper bound of the probability of error. I will write it down later. Okay, thanks, Leo. So now, but I will use this sphere hardening just to give you a geometrical interpretation of Poltirev. Okay, so this is a nice, very nice Voronoi cell. Huh? Of course, in high dimensions, we don't know about this. But probably if the lattice is good enough, you will have almost spherical shape. Okay? So you know about the first radius, the packing radius, and the second one, the bigger one, the covering radius. Now I'm going to use, I think you talk about it in your talk, the effective radius. So what is the effective radius? It's the radius of a sphere with the same volume as the Voronoi cell volume. Okay? Now why? Because in fact the effective radius is related to Poltirev. So you start with a small noise, more noise. Why I'm drawing the noise as a sphere? Because again, remember the noise is almost at a radius of sigma square root of n. Sigma square root of n. Okay? So small noise, more noise, and now you reach the limit. So when the noise reaches the effective radius, you are at the limit. And now what is funny, if you write the volume of the noise ball equal to the volume of the Voronoi cell, you get the 1 over 2 pi e. You get Poltirev limit. Because they are equal in this case. Okay? Now, another lemma, sorry, I need 2 more lemmas before the theorem. This is how to count, I think also we talked about this in the first day, or the second day of this workshop. I have a ball centered on C in dimension n with radius rho. How many integer points inside this ball? We have a nice upper bound. It includes rho, of course, and n. Now, how do I get this upper bound? It's not complicated. I wanted to make a picture, but I have already enough pictures on my slides. You take a cube, let me call it CZ, of volume 1, and you put a cube of volume 1 around each integer point. Okay? How much is the diagonal of this cube? Square root of n. So when you put the cubes around all these points, you will not go outside more than square root of n over 2. So in fact, if you take a ball of the same radius rho, and you add half of the diagonal, you're going to include all the cubes around these integer points in B. Fine, done. Then the number of points is upper bounded by the same ball, but you increase the radius by square root of n over 2, and then you put this outside, done. Now, what do you do with this volume? Stirling formula, you get this approximation. Yes?
I think the covering radius of Zn, right? This is the general...
Yeah, the covering radius of Zn. Yeah, indeed. Yeah, indeed. It's very simple, yeah. Okay, now here we put also Stirling, we put them together. Yeah, we get this ugly formula, but that's fine. The formula is here. Why? Because I need to plug it again in my upper bound later in the theorem, and then a lot of algebraic manipulations before finding that it's going to vanish. Okay? Any other question?
I'm curious about the after, because
Yeah.
this bound is Not tight for it.
Yeah, it's not tight, but it's enough. It's enough for what we're doing. It's more important is the effect of P. I'll show you later in the bound the effect of P. Okay. Now one more lemma. I'm sorry again. Now in this lemma, in fact, what I'm telling you the following. If I have a point here, which is let's say P 0, 0, 0. So one of the components is multiple of P. The point is not going to be in this decoding board. It's going to be outside. So what is this? This is the distance between eta and 0, eta minus 0, greater than the distance between eta and z. And this z has multiples of P. So this is the z I'm talking about, outside in fact. It's going to be outside. Why? Because the probability of this is going to vanish. Now the proof is not very complicated. How do I do the proof? Being far away from z means one of the component, in fact, is greater than P over 2. So think about it like this. This is 0. I'm taking only one dimension, and this is this point, but in one dimension. And then this is P. Then I need just to cross P over 2. I need to cross P over 2 in one direction. Now what I'm going to do, so in one direction. Then I'm going to upper bound by in all directions, n times this probability. And this probability is twice the Gaussian tail function.
Where is that come from in your lambda?
Sorry?
Where does it come from?
Eta is the noise. Eta is, in fact, this is eta. Y is going to be 0 plus eta.
When sigma equal to the one on the top there, you use that sigma?
This is the sigma, okay.
The noise come from the
So eta is eta 1, eta 2, eta n in Rn, and again, and eta I is n 0 sigma square. Okay? Which sigma? I'm using this sigma. Why? Because I want to be as close as possible to Polterev limit to see what's happening at Polterev limit. So I'm taking sigma square equals sigma max 1 minus delta square. Right now I'm putting the delta, but later I need to prove the theorem for any delta. That's fine. Any delta positive. So again, imagine this is the 0. Let me show it here. Huh? This is 0. This is P over 2. This is P over 2. Okay? And then what do you have here? You have a Gaussian noise and 0 sigma square. Okay? What is the probability of the Gaussian noise? Call it eta 1. Eta 1 belonging outside P over 2 minus P over 2 plus P over 2. How much is this? This is twice Q P over 2 over sigma. Q is the Gaussian tail function. Okay? Now, this is just in one dimension. The problem is I don't know how many components are exceeding P over 2 in absolute value. Then what do? I upper bound by n times 2q. Sorry, I wrote it like this to n, but it's n times 2q. Okay? Then again, I'm not using a very complicated upper bound for q. I upper bound q by e minus x2 over 2. This is a well-known upper bound for the Gaussian tail function. And you get this. Now, it's enough to choose p log n, some power of log n. You plug it there. There is a condition on a, on the exponent. It should be greater than 1 over 2r. And then this will vanish. This will vanish. Why this lemma is important? It means we get rid of all points, integer points, which are multiple of p, and which have components multiple of p. Where they are outside this noise ball. Oof. And now why? Because later I'm going to enumerate all integer points inside this noise ball and check if I have a lattice point. If I have no lattice point here inside, it means my error probability is vanishing. Fine, I'm happy.
So that's for the decoding?
This is the decoder. So I'm imagining that my closest lattice point decoder is using this noise ball, this decoding ball. The radius of the decoding ball is sigma square root of n times 1 plus epsilon, because I'm going to take the upper bound, times d1 minus delta also. Okay?
So, I mean, it won't be efficient, right? Your lattice is a very high.
This is a virtual, this is the best decoder we have, closest point decoder. I'm not saying that this is what I'm going to implement in practice. This is a decoder working on the error probability per point. And as I told Chris, that why I'm dealing later with SER, because in my demo I will show you a decoder working in dimension 1 million, but in dimension 1 million I'm not going to do closest point decoder. I'm going to do iterative decoding. It's a local decoder which works on each lattice coordinate, and then I iterate over the lattice coordinate about 40 times to reach 0 in dimension 1 million. Okay? Now, these are just simple bounds, which I'm going to block later. This is a well-known bound. For very large n, when n goes to infinity, the binomial coefficient behaves like exponential in n with the entropy function. And probably you know this bound, of course. Yeah, this is a nice bound. So we have a behavior like 2n h of theta, where h is the binary function, here h of theta. And we have also, if n is small, in fact, this is going to be the n0, the code inside the lattice. We can use this for small n. We have 3 possibilities. Which one is the best? We use the best of them. Okay? So I think now we have almost everything ready to prove the theorem. But what lattice I'm going to build? That's the question. And I need to build LDA lattices or GLD lattices. So first, let me explain quickly what is an LDPC code. So you all know about Hamming codes. It's not important to be Hamming or not. Let's say this is a 7-4 code, and this is the generator matrix of the code. So it means the rows here are the basis of the code as a subspace of F2 to 7. Okay? This is the binary code. And what is H? H is the generator matrix of the null space, of the dual code. Okay, dimension n minus k. Now, for the small codes, I'm not going to use n and k. I should have put here n0, k0 for the small code. Fine. Now, if you look at h, you know that any code word multiplied by h transpose should be 0. So this is the syndrome, the 0 syndrome. Okay. Now, I'm going to build a graph out of h, a graph representation. It's really a powerful representation because it lets you see really how you do the analysis of the code, see how the code is behaving, the cycles in the graph, and also do iterative decoding over this graph. So this is called a Tanner graph. This was proposed by Michael Tanner in 1981, but he also proposed other code structures, graphs. So this is the standard one. What do? On one side, you put the 7 coordinates of a code word. So the 7 coordinates here are associated to the 7 columns of H. Okay? And then on the other side, you put the rows of H. Okay, let me look, for example, at the first row. The first row involves the first column, the third column, the fourth, and the fifth. The first row involves the first column, the third, the fourth, and the fifth. Okay? So it means what in practice? It means that the 7 bits, here these are binary digits. The 7 bits are a code word if and only if C1 plus C3 plus C4 plus C5 equal to 0, and C1 plus C2 plus C3 plus C6 equal to 0. And so in fact, we call these check nodes. Why check nodes? Because the sum of the bits here should be 0 to have a code word. Okay? How do we call these vertices here? We call them bit nodes. Now, I'm not going to deal with the binary codes. I'm going to deal with p increasing with n. Then we're going to call them variable nodes. Okay? So variable nodes on this side and check nodes on the other sides. Now, why I'm talking about this? This is the graph representation, Tanner graph of an LDPC code. Of this code. Now, how do I build an LDPC code? You let the graph, you take infinite number of vertices on both sides. The ratio should be constant. And then, however, you fix the degree of the vertices is finite. You get a low density graph. Why? Because the number of edges is going to be linear in n. not in n square. Okay? Again, if you go back here, if I have a dense matrix H, this will behave, the number of ones will be as n squared. So I'm going to take a sparse matrix H. This is what we call an LDPC code. And this is the first family of lattices. An LDA lattice is when C, the code C used in the construction A, is an LDPC code. So remember, this is what I said. The LDPC code is defined by a sparse parity check matrix. You let n go to infinity, and H is sparse. And you plug the LDPC code here in the construction A. And this is what I call LDA lattice. Why LDA? Low density construction A lattice. What is low density is not the lattice itself. It's the code inside the lattice. Okay, now, many people work on these lattices. The work started almost, like, let's say, 2011 with sparse codes. If you check this paper, appeared in 2018 in the Transaction Information Theory, you will see all the proofs there, but it's a very long paper, very tedious. So we have the proof for infinite and for finite constellations, both of them. Poltirev is reach using LDA lattices, and Shannon capacity. Shannon capacity is when you take a finite number of points in the lattice. Okay? But today I'm dealing only with Poltirev because I'm talking about infinite constellation. Now, the other family of lattices, GLD, this is a little bit tricky. You take lambda 0, and you take a direct sum L times of lambda 0, and then intersection of many direct sums with permutations. So this is the GLD lattice. Now, the simple case, let me take the simple case. With construction A, you take a code C0, L times direct sum, and then you make random permutations of the coordinates, and intersection of J direct sums. Now, 2 direct sums is enough. So these are called GLD codes, and then when you put the GLD code inside construction A, you get also GLD lattice. Okay. Again, we have the proof that we reach Poltirev limit, and as I said, it's slightly better because we are not dealing with finite constellation. That's why P is better. P is increasing as log n instead as n. Probably if we put here the finite constellations, I think the log n will not hold anymore. Okay? And this is again in a paper appeared in August 2019 in the Information Theory Workshop in Sweden. Now, let me show you the example, just simple example of 2 intersections. So you take C0, direct sum L times. So imagine this is C0, direct sum L times. Okay, in my pictures, L is only 2. And then you take in another direct sum of C0. This is the second direct sum. So I have 2 direct sums of C0. Okay, now I'm going to do intersection. What does mean intersection? It means the coordinates of the code word will all, you see here, they are all connected to the first direct sum. What type of permutations here? Just take identity, it's enough. No need to do any permutation for the first one. So here, you see, I'm not putting any permutation here, no need. This is very important, permuting the second direct sum. So this is the direct sum, the second direct sum, and where is the second permutation? It's the matching, the edge matching. So the matching of edges from the left to the right is given by the permutation pi. Do you understand this graph, please? So this graph, this Tanner graph, represents the intersection of 2 direct sums after permuting the second direct sum. This is the permutation, and this is the identity. Is it fine? Now, yes?
Sure, I understand. So the top one is just the code, the parity check matrix of the Tanner graph of the code itself, and the bottom one is the same thing except the coordinates of the code, the left nodes are permuted. Is that?
Yes. Okay. Let me give you a simpler explanation. Now, imagine, forget the 2 rows, take only the first row. What is the first row? It's a simple parity check code. What is the second row? Another parity check code. What is the third row? A third parity check code. Fine. What does it mean you belong to the code? It means the 3 of them should be satisfied. So you are belonging to the intersection of these 3 codes. So what you're doing here, in fact, this is the intersection of the simple code and this simple code, this simple code. This is true for any code, in fact. Now, what I'm doing here, it's more complicated. What I'm doing here, I'm taking not only C0, I'm taking the many C0s, okay? And then the permuted version of these many C0s, the direct sum. Okay? So what does it mean? I have 2 edges per variable. It means this variable belongs to this check node, and this variable belongs to this check node. And of course here, the parity should be satisfied. The sum of, if this is binary, the sum of bits should be 0. But here we're not in the binary case. Here we have a sum with non-binary coefficients equal to 0. The parity check equation is not binary anymore. It's non-binary. Is it fine for this graph? Now, what I'm going to do, it's very tricky, because I have only here a degree 2. So imagine I'm going to take these checks, put them on the left. Take the circles. You see, I take this edge and the second edge and replace this by a unique edge. Where are the circles? The circles will disappear. The circles are here in the middle. Okay? So this is the second Tanner. Is it fine? So you take this, you put them on the left. Now you will have just edges coming from, you will have the check node on the left, the check node on the right, and then the variable node is in the middle, like this. Now take it out, it's fine. Just put an edge. And now where are the variable nodes? No more variable nodes. We have variables on the edges. I have, the code length is n, I have n edges.
So just algebraically, algebraically, right? So the first thing I do is I take the parity check matrix and I create a block diagonal matrix. That's the parity check matrix of the concatenated code. And then I permute the columns of this thing. That gives me another. And then I put one on top of the other. That's it, right?
Bro. So this is exactly H0, 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 H0. So this is the upper half of my bigger parity check matrix. And then what do you do in the lower half? You permute the columns, you put them down. This is exactly what, bravo, this is exactly what we're doing. Yeah, but why I'm showing this graph? Because it's much better to work on this graph.
Yeah. What does the right-hand side correspond to? I mean, I understand what you've done to the graph, but what does it correspond to?
Yeah, that was it.
What is this operation doing?
Sorry, the question?
What does this graph on the right hand correspond to?
On the right hand?
Well, the right half of the slide.
On the right. No, it's the same graph. It is the same. This is the same as that. You know, look, there's one edge like this. I draw it like this, and the circle is here. Then I take out the circle.
Okay.
So the variable nodes are here, are on the edges. Why? Because now I only deal with check nodes. Where are the variable nodes? They are on the edges. Yeah, so this is very special. These graphs do not exist in standard LDPC codes. These graphs exist only in GLD codes. There are no variable nodes anymore, no circles, only squares representing check nodes. Now, where are the variables? They are on the edges. It's the same graph. It's exactly the same graph. Not building another. Is it fine, Chris?
Yeah, I think so.
I mean, again, what I said, you take these squares, put them on the left. How many squares do you have? L, big L squares on the left. And these are the squares on the right. And then you have only one edge going like this, only one edge. So you get this. And now all the analysis is made on this graph. Everything is on this graph.
Can we think of, can we think of there being, are these guys parity checking against each other or what?
Yes, yeah. Now imagine you have a complete graph. Complete. Guess what? Do you see the code if it is a complete graph? Product code. This is the product code. If I put a complete graph here, now, but of course, I don't want to make it, I want a low density graph. I'm not going to make, if you, okay, think about it later. I will show you after the talk. If you put a complete graph here, you get a product code. Ooh. So it means what I'm doing, I'm taking a low density version out of a product code. I'm getting a GLT code, and I'm letting n go to infinity. I'll show you. It's very simple to prove. So believe me, write it down. If the code is, if it is a complete graph, you get the product code. Okay? Now, let me show you quickly the proof. We don't have a lot of time. the proof of the theorem, that these GLD lattices achieve Polterev capacity, Polterev limit, so we can let the error probability vanish for any sigma square less than sigma max. I need a delta. I need a code which we call asymptotically good code, means the Hamming distance of the code should increase as delta n, delta strictly positive. And then we have a small constraint on A, but the constraint comes from the lemma on the points with multiples of P. That's fine. Okay? So I think if you understand just the first page, the rest are just algebraic calculations. Okay? Just understand here the first page. And this is what we talked about already using the noise ball. So I have lattice symmetry. I can assume that Y is 0 plus eta. Okay? So lambda admits the closest point decoder. So this is not a decoder that's going to run here on my Linux in front of you, I hope, in 2 minutes. Okay? Not sure if I can finish this in 2 minutes, but I'll try. The radius of the noise ball, I also call it the decoding ball. Sigma square root of n, I take the upper bound 1 plus epsilon, and I replace sigma by the Polterev limit times 1 minus delta. Okay? So I get this. Now let's say this is kappa, and then the rest is here. I need to plug this in all formulas, the rho. Okay? So the decoding ball will be byn rho, centered on y with radius rho. Now, how can we upper bound the probability of error? Please understand this. This is a very important bullet. Let aleph be the number of non-zero lattice points in B. So this is what I said, non-zero lattice points. If aleph greater than or equal to 1, what does it mean? I have other lattice points here inside the ball. Okay? Now, of course, why this is not inequality? Why this is an upper bound? Because the decoder may decide to choose 0, and then there is no error, despite the presence of another lattice point in the ball. Why not? So that's why this is an upper bound. Okay? So the probability of aleph greater than 1 is this is an upper bound of P. Now, and of course, you can upper bound this by, because this is an integer random variable, by the expectation of aleph. And then how do I find the expectation of aleph? You write it as the sum of indicator function, where inside the ball, for integer points inside the ball, you apply the expectation, and then I get what? PE is upper bounded by the sum of all integer points inside the decoding ball. Sum of what? Probability that this integer point belongs to lambda. So now what do we have here? I have an integer of n coordinates in the space, and this integer is inside the ball. Lambda is random. Why lambda is random? Because the permutation pi inside the GLT code is random, and I can assume that the code C0 divided by H0 is random. Then lambda is random. What is the probability that x belongs to lambda? And that's it. This is what we want to find. Now, probability of x belonging to lambda, later I'm going to write it very quickly. Let me show you. Sorry, here. Here, this part. Probability of x belonging to lambda is the probability that x belongs to all, modulo p, of course, to all direct sums. How many direct sums I'm intersecting? J direct sums. You get this. Okay? So, let me go back. I'm here. So I put them together. So PE is upper bounded by sum. I didn't want to start directly by this, but this is also obvious. The sum or OX belonging to Zn intersection with B. And then now what do? I don't know how to sum over x's inside the ball. These are deterministic points. So what do? We introduce the Hamming weight L. Now we sum over L. We know that L starts from delta n. This is asymptotically good code up to n. And then here we have the weight of x is fixed. Now, why is it interesting to know that the weight of x is fixed? If you look at this sum here, what do you have? We know how many points we have in this ball. Yeah? We know the number of points. But now we are fixing the Hamming weight to L. What does it mean? Now you are going to dimension L. So now the ball is in dimension L, and then you use my lemma on counting points in dimension L, not in dimension n. You go down to a smaller dimension, which is L. So this is going to appear later in the next slide, and then I replace this px belonging to lambda. And now the problem is here. Here I have a step. I don't have time to show it, so this is the miracle in my theorem. I'm going to use something called buckets approach. So this is the sum buckets approach. Given the time, I can see the time there. What do we do in the buckets? Please look at the paper of August 2019. I use the saddle point approach to solve this problem. In fact, we worked together in Qatar with Nordin Mir and Mayara Bolov. We found a way to find this probability of B equal B in upper bound. So if you want to talk about it, I have all the afternoon, no problem, after 3 p.m. So we plug the probability here. At the end, all calculations done. We get a big formula. L is here. L is going to go to infinity like n. And here inside, we have a big function. And the only thing you need to prove that this function is less than 1. Now, what I used to get this formula, we used all the lemma we saw before. All together, all the equations. And this explains also we used also the binomial coefficient upper bounds. That's why you have h here appearing. Lower bounds, also you have h down. So you get big calculations. I'm not showing the steps. And then you prove that this is less than 1. So when L go to infinity, this will go to 0. Okay? Let me show you the same lattice, GLD lattice, J equal to 2, intersection of 2 direct sums. N0 is only 3, and this is in dimension 1 million. And I'm going to go at 0.5 dB decibel from Poltirev limit. So this is what in fact, the curve is here, but I will show you one point. This is dimension 1,000, 10,000, 100,000, 1 million. And what happened at dimension 1 million? We are 0.3 decibel. If you convert to real, this is 93% of sigma max. Square. Sigma square is 93% of, now you may say, okay, is it really very good? 0.3 dB, this is almost the unbreakable limit up to now. Where is the Leach lattice? If you take 24, the Leach lattice is at 4 decibel. It's there. So standard lattices are there. If we take also low density lattices, they are maybe around 1 dB. So GLD and LDA, we were only the unique lattices going so close to Poltirev limit. Okay? In smaller dimensions, you have this. This is the symbol error rate. This is the word error rate, the point error rate. Error rate per lattice coordinate, error rate per point. And this is compare small dimensions, 1,000, 10,000. This is LDA, and notice there is no error floor behavior here because the interleaver, the permutation is optimized. Here I didn't do any permutation optimization. So why we have this behavior? Because we have a Poisson distribution of cycles, and the Poisson distribution of cycles gives you 1 over n. What does mean 1 over n? If I multiply by 10, I go down by 10 every time. Okay? So the demo, this is 1 million. This is dimension, okay, sorry. 1 million minus 1. Why? Because I need to be multiple of 2, or multiple of 3. Okay, so this is, and then the dimension is 2 of the small code. P is 11. It's not a very big P. Huh? So, and then we decode. So now each time you see a line, one line, it means, one line means we went over 2L check nodes. How much is L? You saw the number here. L is 300,000. 333. So we are doing 600,000 check nodes in each line. 600,000 check nodes. It's running on my CPU here. Let me prove it. Top. So it's running on this machine, 100% of one CPU only. 1.5 giga of RAM. It's fine. It's not n square, it's O of n. And then what you see here, the probability of error per lattice coordinate. 500,000 lattice coordinates erroneous. It means at the channel output, more than half of the lattice coordinates are erroneous. Doing round to nearest integer will not work, okay? Then with the iteration, what's happening? After 24 iterations, only 15,000. Okay, it's been what, 1 minute? It will take 40 iterations. Look, it's going down. We reach 0 after 40 iterations. Okay? 1533, 10 to minus 3, 10 to minus 4, and then it goes down very quickly. Now, at the end, sometimes it can stay stuck in 2 lattice coordinates. Why? Because we have a cycle, a butterfly cycle in the graph, if the graph is not optimized. 48, 15 coordinates out of 1 million. Yeah, so that's why 10 to minus 6. It's stuck at 1, 1, 1. It's trying to, oh, now 0. 0, it's over. Okay, so after 40 iterations, all the errors were corrected. So the conclusions. I told you about 1 over 2 pi e. I showed that GLT lattices, using a reasonable value for p, we can achieve the Polterev limit. The complexity, why the complexity is like this, I have time to tell you. It's linear in n, but the p can be, if you increase n0 minus k0, this can be difficult to decode in practice. Now, the questions that you should answer, the audience should answer, applications in cryptography. Thank you. Yes.
If you go to p, which is polynomial in n, do you gain anything anyway?
You don't gain in Polterev because you already have Polterev. You probably gain in the shaping. So it means when I take, yeah. So the Voronoi, why? Because think about it. We said what the code is doing is helping the lattice around the origin. This comes from this lemma. Okay. If you have, the points to be excluded. Okay. So this lemma means the code is good, the lattice is good around the origin. Now, what's happening if you go a little bit further? You have the faces of the Voronoi region. No control on these faces because also p is small. So probably if we do shaping, if we try to be shaping, maybe we will not be able to do 1 over 2 pi e in the shaping. I don't know right now. I don't have the answer. So maybe the value of p, which is increasing in log n instead of n, will make the covering, we call this covering goodness. Covering goodness will not be achievable. So again, this is still an open question. We didn't solve it yet. Any question? Yes.
How big were the codes that you're taking the direct sum of in practice? Like when you're applying the construction, the base code?
The one which is running in practice. So I did the following. So in fact, it's very simple. I took C0 is very simple code, 32 over 11. So this is a parity check code. Then I did Gallagher equation, construction. So I did C0, direct sum with C0. How many times? In the demo you saw is 300,000. Okay, times 3, you get 99999. You get 1 million minus 1. And then this is intersection with a permuted version of the same direct sum. So that's why in the demo, each time we see one error probability displayed, it means we decode here and we decode here. We are decoding 600,000 check nodes at each iteration, corresponding to 1 million lattice coordinates. And 40 iterations. So in the demo, how many lattice points we decoded? What? So I showed you the decoding of 1 lattice point, but this was in dimension 1 million. So it takes 2 minutes in dimension 1 million to decode 1 lattice point. Okay? Thank you.